You have already used this technology today, and almost certainly this week, without ever thinking about it. Pick up a gas lighter or walk over to a barbecue with a push-button igniter. Press it. That click you hear, followed by a spark, is not a battery. There is no battery in there at all. That click is a small crystal being struck, and the impact alone produces several thousand volts instantly from nothing but mechanical force. That is piezoelectricity. And this video is about what happens when you try to scale that from a spark to a power source. And here's the honest part stated up front, because almost nobody covering this will say it. Piezoelectric elements are genuinely poor at generating power. Not modest, poor. The footstep-powered floor that lights a building is one of the most repeated claims on the internet, and the arithmetic does not support it. But there is a real application here, and it is hiding in the second half of the title. Not power, wiring. And once you see what this technology actually replaced, it becomes one of the most quietly successful inventions in any building you walk into. Let me start with the physics, because it is genuinely strange. In 1880, two brothers, Pierre and Jacques Curie, discovered that certain crystals produce an electric charge when you squeeze them. Quartz was one. Press it, and a voltage appears across it. Release it, and the voltage collapses. Press harder, and you get more. They named it after the Greek word for press. What is happening inside is that the crystal has an asymmetric internal structure, with positive and negative charges arranged in a pattern that is balanced at rest. Deform that structure mechanically and the balance breaks, which leaves one face of the crystal positive and the other negative. You have converted mechanical pressure directly into voltage, with no coil, no magnet, and no moving generator. The material itself is the machine, and it works in reverse, which is arguably more useful. Apply a voltage to the same crystal, and it physically deforms. That is how ultrasonic cleaners work, how inkjet printers fire droplets, and how the buzzer in your smoke alarm makes noise. That reverse direction is worth a moment, because it is where this material genuinely earns its living. Every ultrasound scan ever performed relies on it. A piezo element is driven electrically to vibrate millions of times a second, sending sound into the body, and then the same element listens for the echoes coming back, converting those pressure waves into voltage. One material doing both jobs. Sonar works identically, and so does every parking sensor on the back of a car. Inkjet printers use piezo elements to physically squeeze a tiny chamber of ink, ejecting a droplet on demand with extraordinary precision. Quartz watches use the effect in a third way. A tiny quartz crystal is driven electrically and vibrates at an extremely stable frequency. And counting those vibrations is how the watch keeps time. So the material in that lighter is, in different forms, the reason ultrasound exists, the reason your watch is accurate, and the reason your printer works. The first serious application came in the First World War. A French physicist named Paul Langevin used quartz elements to generate and detect underwater sound, which gave the Allies a way to find submarines. That work is the direct ancestor of every sonar system and every medical ultrasound machine in use today. So this is not a fringe technology. It is in your car, your phone, your microwave, and your doctor's office. It is simply almost never used to produce power, and the reason is arithmetic. Now let me show you the numbers, because this is where the footstep dream meets reality. A person walking transfers a certain amount of energy into the ground with each step. Research on footstep harvesting typically puts the theoretically recoverable energy from a single step at somewhere in the region of a few joules at best. And practical piezoelectric systems capture a small fraction of even that. Now compare that to something you actually want to power. Charging a phone battery takes on the order of 50,000 joules. So if a footstep gave you a full joule of usable electricity, which is generous, you would need something like 50,000 footsteps to charge one phone. That is a person walking continuously for many hours, on a tile, for a single charge. And the real figures for piezo elements are considerably worse, since a typical disk produces energy measured in millijoules per press. This is why the most famous company in this field quietly changed direction. Pavagen, founded in the UK in 2009, is the name attached to nearly every footstep power story you have ever read. They have installed tiles in shopping centers, airports, and city streets, and in 2014 they lit a football pitch in a Rio favela, partly from the players' own movement, which is a genuinely lovely piece of engineering, but their tiles move toward electromagnetic generation rather than relying on piezoelectric elements. Instead of squeezing a crystal, the tile depresses slightly and spins a small generator, because a magnet moving past a coil produces far more energy than a crystal being pressed. That is the honest state of the art. The leading company in footstep power largely stopped using piezo for power because piezo does not make enough of it. Railway stations in Japan trialed piezoelectric flooring in the 2000s in some of the busiest passenger environments on Earth, and the output was small enough that it remained a demonstration rather than an installed technology. So if you're watching this hoping to floor a hallway and run your lights, I would rather tell you now, that is not what this does. Here is what it does, and it is genuinely excellent. Walk into a modern commercial building and look at a light switch. In a growing number of them, that switch has no wires running to it and no battery inside it. When you press it, the press itself generates enough energy to power a tiny radio transmitter, which sends a signal to a receiver that switches the light. One press, one burst of energy, one message. There's nothing to wire and nothing to replace, ever. A German company called Ocean built an industry on exactly this, and battery-free wireless switches are now installed in large numbers in offices, hotels, and commercial buildings worldwide. Think about what that solves. Running a cable to a light switch means cutting a channel in a wall, and moving that switch later means doing it again. A battery-powered wireless switch avoids the cable, but creates a maintenance problem. Since a building with 2,000 switches has 2,000 batteries, somebody must eventually change. A self-powered switch has neither. You glue it to the wall, and it works for the life of the building. That is the genuine application of this technology, and it is why the second half of the title is the important half. Not free power, no wiring. The same principle appears elsewhere once you know to look. Tire pressure sensors, vibration sensors on industrial machinery that report their own condition, structural monitors embedded in bridges. In every case, the device needs a tiny amount of energy occasionally in a place where running a cable or changing a battery is expensive or impossible. Piezo is not a power source. It is a way of removing wires and batteries from small sensors, and by that measure it has been an enormous success that almost nobody notices. Now let me show you how to build one, because this is genuinely worth doing. The core component is a piezo disc, which is the same element used inside cheap buzzers. They cost roughly $1 to $3 each, and a pack of 20 runs $10 to $15 from any electronic supplier. Each is a thin brass disc with a ceramic layer bonded to it and 2 wires attached. You will also need a bridge rectifier, costing about $1, and this part is not optional. A piezo element produces a sharp voltage spike when compressed and an opposite spike when released, meaning the output is alternating and messy. The rectifier turns that into usable direct current, and without one you will store almost nothing. Then a capacitor to accumulate the charge, since no single press produces anything useful. The capacitor collects many presses into one meaningful amount of energy, which is the whole architecture of every harvesting system on Earth. Trickle in, store, release in a burst. Then an LED to show you it works, and optionally a small boost circuit at $5 to $10, which takes the low voltage and lifts it to something a device can use. For the plate itself, 2 pieces of plywood or acrylic with the discs sandwiched between them, separated by thin foam so the discs flex rather than shatter. Wire the discs in parallel to add their current together. Total cost lands around $20 to $30, and the result is a plate that flashes an LED every time somebody steps on it, powered by nothing but the step. That is a genuinely satisfying thing to build, and it is an excellent demonstration for anyone learning electronics, particularly children, because the effect is immediate and obvious. If it does not work, there are 3 usual causes. You may have skipped the rectifier, which is the most common mistake. A piezo output is alternating, and an LED only conducts one way. So without rectification, you lose half of what little you had. Your discs may be clamped too tightly. The ceramic has to flex to produce anything. So a disc glued flat to a rigid board between 2 hard surfaces cannot deform and will produce almost nothing before it cracks. Or you may be measuring wrong. A multimeter set to volts will show you a spike so brief that the display never catches it, which makes people conclude the plate is dead. Charge a capacitor over 20 or 30 presses and measure that instead, since the capacitor is what actually accumulates the result. Now the limits, honestly. The output is tiny, and I have given you the arithmetic. Expect an LED flash, not illumination. Piezo ceramic is brittle, which is the practical failure mode. These elements are designed to flex slightly, not to take the direct weight of an adult, and a disc under a heel with no support will crack. Proper designs support the disc around its edge and let the center deflect a controlled amount. The output is also a spike rather than a flow, which is why the rectifier and capacitor matter so much. Wire an LED straight to a piezo disc, and you will see a flicker and nothing else. And the honest comparison is unforgiving. For $27, a small solar panel produces vastly more energy in a single afternoon than a piezo plate will produce in years of footsteps. If you want power, buy the panel. The safety picture is the simplest of any project in this series. The voltages can be surprisingly high, since an igniter crystal produces thousands of volts, but the current is negligible, which is why a lighter click startles you and nothing more. The one genuine caution concerns the material itself. The ceramic in most piezo elements is lead zirconate titanate, which contains lead. Handling intact discs is fine, but do not sand, grind, or cut them, and do not let children put them in their mouths. Dispose of them as electronic waste. The ledger for the whole story, then. 20 piezo discs, $10 to $15. A bridge rectifier and capacitor, $2 to $3. An LED and wire, a couple more, Plywood or acrylic for the plate and some foam, $5 to $10. Total, roughly $20 to $30. For a working demonstration of a principle discovered in 1880. Here's the thing worth keeping from all of it. The Curie brothers found that squeezing a crystal makes electricity, and within 40 years that discovery was hunting submarines. Within a century it was in every lighter, every ultrasound machine, and every inkjet printer on Earth. And then, in the last 20 years, somebody looked at it again and asked whether it could power a building from the people walking through it. The answer turned out to be no, and that would be the end of the story except for what came next. Because the same people noticed that while a press cannot light a room, it can absolutely send a message. And a switch that needs no wire and no battery is worth more to a building than a floor tile that produces a flicker. That is a pattern worth recognizing. The application that made this technology genuinely useful was not the impressive one. It was the modest one that solved a real problem nobody had framed as an energy question at all. Everything this channel has gathered on trickle power sources, the harvesting circuits, the storage, the real numbers, and the real limits lives in one place linked right below. And the comments are where this one earns its keep. Has anyone here built a piezo plate, and what did your meter actually read? And if you have ever used a battery-free light switch without realizing what was inside it, tell me, because most people never notice. As for the cell that runs on living bacteria and ordinary mud, discovered in 1911 and still producing power months later without being touched, that is on screen right now. Different trickle, same problem. Till next time.